Let's talk about bijective functions. A bijection is a function that is both a surjection and an injection. What this means is that every element of the codomain has exactly one pre-image. So let's go over our first example, the identity function over A. So we have, it goes from A to A, and we assign X to itself. And this is a bijection because we have a one-to-one correspondence. Okay, bijective function is a one-to-one correspondence. If those are my two sets, now every element of A has exactly one pre-image, which is the same element. So we say that it is a one-to-one correspondence. Let's go over a more interesting example. We'll start with the natural logarithm function, which starts from the positive real numbers and goes to the real numbers, and we're assigning x to ln of x. Now, just to refresh your memory on what this function looks like, it goes from down below, and it looks like it has an asymptote, but it just increases very slowly. Now, this function goes hand in hand with the exponential function, which this one goes from the reals to the positive real numbers, and we're assigning x to e to the x. Now they go hand in hand because they are inverses of each other. They are inverses of each other. What I mean by that is if you take ln of e to the x, you're going to obtain x, and if you take e to the ln of x, you're going to obtain x again. So this means that they are inverse to each other, and I'm just going to hint at a theorem that can be used to prove that those two functions are bijections. A function is a bijection if and only if it is invertible. So this is a theorem that's going to be very useful. Once you know a few results, you're going to be able to view the video on this theorem. So the exponential function and the natural logarithm function are inverses of each other. So that means they are both invertible, and then you can use this implication of the theorem to conclude that both functions are bijections. For our third example, let's go over a function, and we're going to prove that it is both a surjection and an injection. So we'll start with f from r to r, and we're going to send x to a times x plus b, where a is a non-zero real number and b is a real number. So we'll start with injection. We need to prove that f is an injective function. And for that, we're going to need two real numbers in the domain. So x1 and x2, which are real numbers, such that they are mapped to the same element. So f of x1 is equal to f of x2. Now, I just want to visualize, give you a visual idea of what we're going for here. We're starting with a single element in the codomain, an arbitrary element in the codomain, which has at least one pre-image. So this is our single element, okay? Those two objects are equal. And we have x1 and x2, which are both mapped to that object. Now our goal here is to prove that x1 and x2 are equal, because this would mean that it has at most one pre-image. Now what we can say from our equality, f of x1 is equal to a times x1 plus b. I'm simply using what our function f sends x to. And f of x2, this is going to be a times x2 plus b. And now those two are equal, so we can say that those two are equal. And this implies what we can do at this point is we want to isolate x1 and x2. We can use some simple high school algebra, subtract b from both sides, and we're going to obtain a times x1 is equal to a times x2. And since a is distinct from 0, it has an inverse for multiplication. So you can multiply both sides by 1 over a, but this is only because a is distinct from 0. So we multiply 1 over a to both sides, and we'll obtain what we wanted. x1 is equal to x2. Let me bring that down, and we have f is injective. What about surjectivity? We want to show that f is surjective, and for that we're going to need an arbitrary element in the codomain, and we're going to show that this arbitrary element has a pre-image. Now, a little trick that we can use is suppose that we do have a pre-image for that arbitrary element. So suppose there exists an x that is a real number in the domain such that x is the pre-image of y. So f of x is equal to y. Then what we can say is, since we have f of x is equal to y, f of x, this is equal to a times x plus b. And again, what we want is to find the pre-image of y. So we need to find the value of x. Let's say that f wouldn't be a surjective function. You can still suppose that there exists one, and you're going to arrive to a contradiction. By trying to isolate x to find the value of x, at some point you're going to run into a certain problem. You're going to have to divide by 0 or something like that, and this will give you some ideas of how to form a counterexample. Now, in this case, f is surjective, so we're not going to find a counterexample. It's not going to lead us to a counterexample. We're actually going to obtain the value of x. So we'll subtract both sides by b, and then multiply both sides by 1 over a, and we can do this again because a is distinct from 0. This will yield x is equal to y minus b over a, and this is exactly the pre-image of y. We can verify this. F of minus y minus b over a, this is equal to a times y minus b over a plus b. Now the two a's cancel out, so we're left with y minus b plus b. The b's cancel out, and we have y, our arbitrary element. So y was arbitrary, which means that it works for every element in the codomain. Every element in the codomain has a pre-image. Hence, f is surjective. We had shown that f is injective, which means that f is bijective. Okay, it is bijective.